welcome back to Physics 425. We're kind of in the middle of our discussion of some concepts from statistical mechanics, and in the last video we talked about the canonical ensemble, which led to discussions about the Boltzmann distribution, the partition function, and the Helmholtz free energy. The Helmholtz free energy was particularly nice because it was this link between the quantum mechanical partition function, which involves a sum over the available quantum states to the system, and the macroscopic thermodynamic behavior of the system. Today, we're going to talk about the grand canonical ensemble, and it's like the canonical ensemble where we have replica systems in thermal contact with one another so they can exchange energy, but this time we'll also let the replica systems exchange particles, and so no single member of this ensemble will have a fixed number of particles. So a lot of the analysis we'll do will be quite similar, in fact, to what we did in the previous video. Before we get into that, let's just remind ourselves of one concept, and that is the concept of the chemical potential. So if we add or remove particles from a system, then we expect there to be an associated change in the internal energy of the system. And so in that case, what we could do is we could write the internal energy as a function of entropy and volume, and now we're going to add particle number, so that when we take a differential, what we'll get is a du ds term at constant v and n, and a du dv term at constant s and n, and the new term is a du dn term at constant s and v. And we can compare this to what we would expect for from the first law of thermodynamics, which is dq, which we can write as TdS, and then a minus PdV, which is the mechanical work. And now what we're going to do is we're going to add a chemical work. And so here we have, let's say, heat, mechanical work, and chemical work. I'm going to call this equation star because we're going to come back to it in just a moment. And so what we can do is we can compare these two expressions for du, and we can identify this partial derivative, the coefficient of the ds, as temperature, this coefficient of the dv as minus the pressure, and this coefficient of dn as mu, which is the chemical potential. Okay, so mu is equal to du dn at constant s and v is the chemical potential. We can see that du is clearly a change in energy, and so it has units of joules or some other energy units. dn is a change in particle number, and so it's dimensionless, and so this coefficient, the chemical potential, must have the units of energy. And so mu, units of mu, is equal to energy. Okay, from equation star, we could write a different expression for mu. So let's imagine a process at constant u and constant v. And so then the du term vanishes and the minus p dv term vanishes. And then in that case, we could write mu as minus t times the partial derivative of s with respect to n. So we could write mu is equal to minus t partial derivative of the entropy with respect to n when internal energy and V are constant. That's going to be useful for us because, as we saw in the last video, what we're able to do with these ensembles is to come up with expressions for entropy. And so if we come up with an entropy expression, we could take derivatives of it, and perhaps we can find the chemical potential. Okay, so that was a little recap of some things I think we've seen before. And so now let's get back to the grand canonical ensemble. So before getting into some of the technical details, let's just recap some of the things we've seen already. We started with this microcanonical ensemble. And in that picture, we had these replica systems that were isolated from one another. And so that means each member of this microcanonical ensemble had a fixed energy and a fixed particle number. So microcanonical ensemble. This is a collection of replica systems, all isolated from one another. One of the results from the microcanonical ensemble was that the entropy for these isolated systems could be written as Kb ln W. Okay, second, and in fact in the last video, what we started thinking about was replica systems that form an ensemble, but they're in thermal contact with one another. And so they're all at the same temperature, but one system can exchange energy with other systems in this ensemble. Canonical. Ensemble. So here we had a collection of replica systems in contact with a thermal reservoir. So if you're thinking of one particular member, say system A, then the thermal reservoir is all of the other systems in the ensemble. Okay, so in this case, energy can flow in and out of the individual systems. However, the overall ensemble is isolated, and so it has a fixed energy. Okay, and so now what we're going to talk about is the grand canonical ensemble, and I'm going to use dashed lines. So what these dashed lines are supposed to represent are systems that are again in thermal contact with one another, and they can exchange energy, but the dashed lines allow particles to pass through, and so any particular system inside the ensemble can have particles added or removed. If we're thinking of one individual system, then all the other systems form the reservoir for this individual system, say system A, and what we can do is we can add or take energy from this reservoir without significantly changing its temperature, or we can add or remove particles from this reservoir without significantly changing its chemical potential. Okay, so this is going to be the grand canonical ensemble, and it's a collection of replica systems in contact with a thermal reservoir and a particle reservoir. Energy and particle number. Maybe let's say energy and particles can be exchanged among the replica systems. Okay, however, the entire ensemble has, again, a fixed total energy and a fixed number of total particles. Okay, so in the grand canonical ensemble, if we take a particular system, and so let's say we have system A, the energy and particle number of each replica system can change. But the energy and particle number of the ensemble as a whole are fixed. And so we'll say that the energy of the ensemble is UT and the number of particles in the ensemble are NT. Okay, so let me just write down this modified first law of thermodynamics again. du is TdS minus PdV, and the new term is mu dN, this chemical work. So for the reservoir, we know that it's entropy because it's an isolated system, the overall reservoir. We can write its entropy as Kb ln of W. Now, 1 over T could be expressed as ds du. I'll put subscripts R because we're talking about the reservoir. And so this is true if we hold the volume and particle number of the reservoir fixed. Okay, so then that is Kb d ln Wr. So I'm just substituting in for the entropy Kb ln Wr and dur and fixed volume and particle number. So I'll call this star. I think, did I already use star for something? Yeah, but so, okay. We use this for star here, so we'll call this something else. Exclamation mark. All right. So let's go back to star and let's see if we can write the chemical potential in terms of a derivative of the entropy. So what we're going to have to do is we're going to have to hold V and U equal to a constant, and then if we solve for the chemical potential, it would be minus T ds dN. And again, that's a constant volume and constant internal energy. Substituting S is Kb ln W, we're going to get minus Kbt d ln Wr dNr. Now this is at constant V and constant internal energy. We'll call this number sign. So these two expressions are coupled differential equations. However, they're relatively easy to solve for the ln of W. so the solution of these two equations is ln of WR is equal to K. This is going to be some constant plus UR minus mu NR over KBT. Okay, you can almost do this in your head. You could verify that that's true if we go to the first equation and put in for ln WR K, a constant, plus mu R minus mu NR over KBT. When we take the U derivative, we just get 1 over KBT, and the KB's cancel and get 1 over T as expected. For equation number sign, when we take the N derivative, we get minus mu over KBT. The minus and the KBT's cancel, and we just get the chemical potential as expected. Okay, so that works. What we could do then is we could exponentiate and solve for WR. We get e to the k, which I'll define to be some other constant, alpha, and then we'll have to multiply that by the exponential of UR minus mu NR over KBT, where alpha is e to the k is some other constant. Okay, so we go back here and we isolate one of these systems, the red system, system A, and we say suppose system A has energy UA and NA particles. Okay, and so what we're going to do, looking ahead here, is we're going to say we're going to pick a particular state for system A, and then we'll analyze how many quantum states are available to the reservoir, and then we'll sum over all the possible states of A and get the total number of quantum states available. We'll take the ratio of the two to get a probability, just like we did in the previous video. Okay, before we do all that, let's make the point that the reservoir can add or remove a small amount of energy without changing its temperature. And so that means that, well, and we can also write that the energy of the reservoir is the total energy of the ensemble minus the energy of system A. The other thing the reservoir can do is it can add or remove a small number of particles without changing the chemical potential mu. And the number of particles of the reservoir is equal to the total number of particles in the ensemble minus the number of particles in system A. And so we'll eventually, very shortly, take these expressions for UR and NR and sub them into our WR that we just calculated. In fact, let's do that right now. So WR is equal to alpha, which is a constant. And so we're going to have an exponential of UR, which we'll write as UT minus UA, minus the chemical potential mu times nr, which is nt minus na, all over kBt. Okay, we can separate this expression into a product of exponentials. So one will be an exponential involving the totals, so total internal energy and total particle number of the entire ensemble. And then the second exponential is going to involve the energy and particle number of system A. And I have to sneak in a 1 over kBt here. Okay. Now, what I'm going to do is I'm going to take all of the stuff involving the total quantities for the entire ensemble and just define that as a new constant, alpha prime. And so what we get then is WR, the number of quantum states available to the reservoir, is some constant times e to the minus UA minus mu NA over kBt. So this is the number of possible states for the reservoir when state A has energy UA and particle number Na. All right. So that's just the reservoir. The total number of states available to the combined system, and the combined system is the entire ensemble. So it consists of state A and the reservoir made up of all of the other states. Is W is WA times WR. And so now what we're going to do is we're going to do something like we did for the canonical ensemble, and we're going to say, well, what if A is restricted to be in a state phi I with energy UI and particle number Ni? Then WA is just 1, right? We've selected a particular state. So if A is restricted to be in one particular state, phi I with energy UA is, I think we used, well, I'm going to follow my notes. I think last time we used EI. I'm going to use UI so I don't mess up my notes here. And NA is equal to NI. Then WA is just equal to 1. We've picked exactly what its state is. And that means that WI is equal to 1 times WR. And so WI is the number of states of the combined system when we've forced system A to be in state phi I. Okay, so then in that case, WI is equal to alpha prime e to the minus UI minus mu Ni over kBt. What we did last time, you may remember, is we said, okay, now if we relax this constraint and allow system A to have any energy and any particle number, then we just sum over all those possible states, and then we get the total number of quantum states available to the entire ensemble. So the total number of available states to the combined system is. So we sum over all of the possible states of system A. So sum over all possible states of system A. And so this means this is a sum over all possible energies and all possible particle numbers. Okay, and so that's going to be alpha prime, which is a constant, so we take it outside the sum over J, e to the minus uj minus mu nj over kbt. So now we have two expressions. One is the number of possible states of the ensemble when system A is forced to be in a quantum state phi I, and the number of possible states for the entire ensemble when system A can be in any state. And the ratio of those two tells us the probability that we'll find system A in a state phi I. So, of all possible states W, the probability, say Pi, of being in state phi I is, okay, so Pi is Wi over W, and that's equal to, when we take the ratio, the alpha primes are going to cancel. Okay, and so all that we're going to be left with is e to the minus mu I over mu, ui minus mu ni over kbt divided by the sum of that same thing. Okay, so this is called the grand canonical distribution function. I'm going to switch color here, and I want to compare this to what we found for the canonical ensemble. So for the canonical ensemble, ensemble, we had something that looked pretty similar, except we didn't have the particle number involved. But other than that, it looked the same. We had a nicer name for this. This was the Boltzmann distribution instead of the grand canonical distribution function. Okay, so I'll go back to black, which will be results for the grand canonical ensemble. So what we can do is we can define the grand partition function. And the grand partition function has a funny symbol. It's a Greek letter chi, and so this is capital Greek letter xi, and I think it's properly pronounced as chi. Okay, and so the grand partition function is just the denominator of the probability above, and so it's the sum over j of e to the minus ui minus mu n, it's j, uj minus mu nj over kbt. Okay, so for the canonical ensemble, we also had a partition function, and so it was given the symbol z, and it was a sum over j of e to the minus uj over kbt. Again, in the last video, I think we used ej, but it's the same thing. So this was the partition function. What we were able to do in the previous video was to relate the partition function, which is a sum over all quantum states, to thermodynamic variables. And so we're going to do something similar with the grand partition function. Okay, so what we can do then is we can say that pi for the grand partition function is e to the minus ui minus mu ni over kbt divided by the grand partition function. All right, we previously showed for the canonical ensemble that the average entropy per member in the ensemble was given by minus kb sum over I of pi ln pi. So this probability is used to determine the entropy. We could go through exactly the same type of argument, which I'm not going to repeat, but the argument follows the exact same line of reasoning for the grand canonical ensemble. So this result is also true for the grand canonical ensemble. Of course, the only difference is that we have to use the new form of the probability of a system being in state phi I. Other than that, it's the same. And so this follows by the exact same arguments. Okay, so the entropy then is minus kb sum over I of pi, and then we're going to take the ln of pi. The ln of pi is going to give us minus ui minus mu ni over kbt, so it's minus ui minus mu ni over kbt. And then we have minus the ln of the grand partition function. Okay, So let's see, we can distribute the sum, and what we end up with is in the first term the kb's cancel, so we have 1 over t, the minus signs cancel as well, sum of I pi ui, and then we have minus mu over t, sum of I pi ni, and then we get a plus kb ln of the grand partition function. As before, this is the average internal energy of a system, and this is the average particle number in a system. And so therefore, what we end up with is S is equal to U bar over T minus mu n bar over T plus kb ln K. So if we multiply by T and then solve for, let's say, minus kbt ln of the grand partition function, we would get minus kbt ln K is equal to, let's see, it's U bar minus mu n bar plus, no, we have to subtract S minus T times S. This is called the grand potential. So it's given capital letter phi with a subscript g, and this is defined to be minus kbt ln K, which is equal to U bar minus mu n bar minus TS. And so this is the grand potential. It's analogous to the Helmholtz free energy. F is minus kBT ln Z is U minus TS for the canonical ensemble. Okay, so let's emphasize this result as well. So the last thing I'll do for today is just try to relate this grand potential to some thermodynamic variables. Okay, so let's think about this grand potential. Again, remember, it's the sum over available quantum states. So it's this microscopic quantum mechanical quantity, which is U bar minus TS minus mu n bar. And so this is the Helmholtz free energy part. And so that's minus kBT ln of the grand partition function. Okay, so if we take a differential, that's going to be du bar minus T ds minus s dt minus mu dn minus n d mu. Okay, so du is TdS, the heat, minus PdV, the mechanical work, plus mu dn, the chemical work, and then we still have minus TdS minus SDT minus mu dn minus n d mu. Okay, and so there are some cancellations. The TdS cancels, and the mu dn cancels. So what we're left with is d phi g is minus pdv minus sdt minus n d mu. Okay, so that means, let's see, entropy. If we keep volume and chemical potential fixed, then entropy is equal to minus d phi g dt at constant v and mu. Pressure. If we keep T and mu fixed, then we get minus d phi g dV at constant temperature and chemical potential. And particle number. If we keep V and T fixed, this is minus d phi g d mu at constant V and T. In fact, this one is going to be particularly useful in the next video, and so we'll come back to it. But for now, the main point is, once we know the grand partition function, we can calculate the grand potential and therefore the thermodynamic quantities or properties of our system, which has now variable energy and variable particle number. Okay, good. So that's where we'll stop, and we'll pick it up next time. In fact, I think next time what we'll be able to do is we'll be able to derive, using the ideas from the grand canonical ensemble, we'll be able to derive the expressions for the Fermi-Dirac distribution and Bose-Einstein distribution, which we've already used when looking previously in this course. Okay, and so that's what we'll try to do next time. Thanks very much.